Welcome to Plutus IAS, and today we are covering use of LTA as a decarboxylating agent. Although we have already covered the use of LTA multiple times, but this one is particularly very important. Why? Because it involves different compounds, and that a lot of variation for this specific case of using LTA as a decarboxylating agent can be made. Okay, so what today we will do, we will first learn the use of LT as a decarboxylating agent. That means we will be using it for the removal of CO2 from a molecule. Now, which type of molecule we will be utilizing, which molecules are inert towards it, for which we need special conditions, and one example how to specifically use it. So without wasting any time, let's move forward. So the first example we are trying to cover is for your alpha hydroxy acids. Alpha hydroxy acids. So for alpha hydroxy acids, this is a common example for your alpha hydroxy acid. If I use LTA, which is lead tetraacetate, over it, it will give me aldehyde or a ketone based on whatever the type of substitution it has. Okay. Now, how this particular result can be obtained can be explained in the terms of mechanism. So, for our mechanism, what do we know? We know that lead tetraacetate, RCOH, and this will be C double bond OOH with lone pair, and we'll be utilizing lead acetate, PbOAC, whole thrice, and one of the OAC like this. So what happens? Since OAC is a good leaving group, it will take the electron density and will leave as OAC minus. This oxygen will attack the lead so that it can fulfill the electron density that is being withdrawn by the OAC. Later on, after this oxygen will get positively charged. So what will it do? It will get positively charged. So it will take its electron density from H, removing first mole of acetic acid. Later on, now it has formed RC R dash O H right here with carbon double bond O PB OAC whole twice, and let's write one of the OAC simply like this, double bond O CH3. So what will happen? A similar scenario will occur. A similar scenario will occur where this lead will take electron density from this oxygen. This oxygen, wait, wait, here, yes, this carbon here, this oxygen will take its lone pair, attack this hydrogen. Wait, here should be one more O. Here it should be one more O. So this oxygen will attack this hydrogen. The oxygen will shift its electron density from hydrogen to the carbon side. This lead will take the electron density. This oxygen will take it from here to balance it. Now, this CO2 to fulfill the charge density which is being withdrawn by the PbOA whole twice, here it will withdraw the electron density from the carbon, shifting it to the oxygen side. Here, this will enable us to remove the first mole of CO2 and one mole, the second mole of ACOH, and we will get ketone. Ketone or aldehyde depends on the substitution of the alpha hydroxy acid that you have taken. Now, another example can also be derived by using similarly, a similar mechanism can be followed if you are using alpha keto acid. Alpha keto acid. So if you are taking alpha keto acid, it will look like this. COOH. If you are using LTA over it, it will give you 2 moles of PB. Sorry, not 2 moles. It will give you COOH, 1 mole of CO2, 2 moles of ACOH, and 1 mole of CO2. Now, the reaction usually do not occurs like this. Why? Because alpha keto acids, alpha keto acids are inert towards the presence of towards the presence of LTA. So how can I do this conversion? So for this conversion, LTA, unless you add another reagent, unless H2O or alcohol are used as a solvent. This conversion will never take place unless here your examiner gives you written H2O or some kind of alcohol. Only then this reaction can take place, otherwise it won't be taking place. So there are two cases, one for your alpha hydroxy acid, second is for your alpha keto acid. For alpha keto acid, we need to define that the conditions are very necessary. If the conditions are not present in this scenario, LTA will not react and you will never ever get a carboxylic acid. Now, let's try an example from a previous year question. We are given COOH and here we are given double bond oxygen. On use of LTA, we need to write what will be the product that is being formed here. So we know LTA in presence of a carboxylic acid, naturally it will undergo decarboxylation. So we already know the mechanism for it. So the mechanism you would expect that CO2 will leave and it will give you this compound. Most people think since it's working like a decarboxylating agent, the H will be acting like this and you will get this compound, but this is entirely wrong. This is not our product, at least not the major one. So how can this be achieved? So we'll take this molecule back here. Again, use LTA. Oh, we know after the attack it will be PBOAC whole twice. I can write as like a previous case, C double bond O CH3. What will happen? This carbon will shift electron density to oxygen side. The lead will take electron density, it will remove. So from which side it will attack the hydrogen? So clearly we can see that here the hydrogen which is attached here is between two electron withdrawing groups. One is a carbonyl which are applying minus I effect and this carbon. Hence, these two hydrogens which are present on this carbon, they are acidic in nature. Hence, OAC can easily attack one of the following hydrogen N. So, this hydrogen's electron can be shifted to this bond, which will give us our ultimate product, which is this one. This is our major product, which is what? This is an alpha beta unsaturated ketone. Unsaturated ketone. So what do we came to understand? We came to understand that LTA can not only give you aldehydes or ketone, but is also capable of giving carboxylic acid as well as alpha beta unsaturated compounds. So what type of product that you wanna get from the reaction? It entirely depends on which type of reactant you are given. If the reactant is an alpha hydroxy acid or alpha, then most likely you will get a ketone, otherwise an aldehyde. If it is an alpha keto acid, then you need to look for the condition which is being provided. If the condition is not being provided, you will simply write that no reaction will take place. Third case, which is this particular example which we have seen, if you are given a cyclic compound with attached COOH group, in such case we will see that mostly after decarboxylation a double bond would have been formed and it would result in the formation of alkene. But since in this case I had a carbonyl group nearby, this compound that I've got is nothing but alpha beta unsaturated ketone. So I hope this would have cleared you majority of the doubts regarding the use of LTA as a decarboxylating agent, how can be used, which are the condition, as well as the examples which demonstrate that the use of LTA can be very useful for obtaining different compounds. So in case of any doubts, you can add it to the comment section and we'll get back to you. And from next video, we'll try to cover other carboxylating examples as well. So today, let's end this here and we'll see you in the next video. Thank you for joining us.